Can everybody hear me? Is the mic turned on? Yeah, okay. So welcome to Oral Session 5D. My name is Matthew Blaschko. I'm the session moderator. We have 6 rather interesting talks on optimization and theory in this session. And so without further ado, I think we can already start with the first speaker, if you can come up to the stage. Hi. And so the first talk is called Tight Lower Bounds under Asymmetric High-Order Hölder Smoothness and Uniform Convexity. And it's going to be given by Cedar from Purdue University.
Oh, there we go. Yeah, great. Okay. Good morning, everyone. Thanks for joining this session. It's great to see such a big crowd here for a theory talk. I actually paid 30 of you to come. Next time I'll pay 40. Yeah, just joking. If you didn't intend to be at a theory talk, well, please don't run. Just fasten your seatbelt and bear with me for 10 minutes. I'm sure the rest of this session will just get more and more interesting from here. So my name is Cedar Bai. You can call me Cedar or Cedar. I'm from the Department of Computer Science at Purdue University. Today I'm presenting our paper, which is joint work with my advisor, Professor Brian Bullins. In this paper, we establish the tight lower bounds on the oracle complexity of optimizing high-order Hölder smooth and uniformly convex functions. To start with, let me elaborate that by oracle complexity, we mean the number of times an algorithm queries an oracle to obtain an epsilon approximate solution. For example, a first-order oracle returns the gradient or subgradient of a function. In the convex and smooth setting, the first-order oracle complexity to reduce the optimality gap scales with 1 over epsilon, which this concept is also closely related to convergence rate, which characterizes how fast the error decays with the iterations. But we will stick to oracle complexity in this talk. Now, to introduce our general setting, let's begin with smoothness, which many of you may be familiar with. Smoothness means a function's gradient is L-Lipschitz continuous. Also, there is an alternative definition using the first-order Taylor expansion. Hölder smoothness generalizes smoothness by adding a fractional power, nu, in the range from 0 to 1, interpolating between smooth and non-smooth functions. When nu is 1, the function is smooth. When nu is 0, the function is non-smooth. Orthogonal to this, high-order smoothness generalizes to functions with high-order derivatives. For example, p-order smooth requires the p-order derivative of the function, which is a tensor when p is larger than 2, to be Lipschitz continuous. Combining them, high-order Hölder smoothness means the p-order derivative is Hölder continuous with parameter h and degree nu. Now, moving on to uniform convexity. The basic concept of convexity is well known. The function lies above its tangents, or the gradient is monotone. Strong convexity strengthens this by enforcing at least a quadratic growth. And uniform convexity generalizes strong convexity by allowing the growth to be other than quadratic, specifically as a qth power on the norm with parameter sigma and degree q being larger than 2. Now that we have seen the definitions of high-order Hölder smooth function, high-order Hölder smooth and uniformly convex functions, you may wonder, why do these properties matter? Let's look at the example of cubic regularized Newton method, a common algorithm in machine learning. In each iteration, it solves a subproblem minimizing a second-order Taylor expansion, which we denote as capital F, and we wish to find the argmin of capital F. This function is uniformly convex with degree 3 and it is also second-order smooth, or Lipschitz Hessian. Here, Q equals P plus nu. Gasnikov et al. Showed that if we exploit the Lipschitz Hessian property and apply some optimal second-order method, we achieve linear convergence with m over sigma, which is the second-order condition number to the power of 2/7. However, computing the Hessian is expensive, costing us big O of dimension squared. So we may prefer to use first-order methods instead, which cost us only big O of d computation. In that case, the oracle access is limited to the first order. While the function is still uniformly convex with degree 3, it can be only regarded as first-order smooth in terms of convergence analysis, creating a mismatch here. Existing results show that the first-order complexity in this setting is square root of the first-order condition number times 1 over epsilon to the power of 1/6. This actually raises a general question. For arbitrary combinations of this P, Q, and nu, what is the p-order oracle complexity? Song et al. Recently proposed a uniform algorithm with upper bounds for all such combinations. In the symmetric case, when Q equals P plus nu, their method achieves linear convergence. When Q is larger than P plus nu, the complexity is polynomial in 1 over epsilon. For Q being less than P plus nu, the complexity involves both the polynomial of high-order condition number and a quadratic convergence term. Their framework generalizes many existing low-order methods. In this work, we provide the matching lower bounds in the two asymmetric cases, Q being larger than P plus nu and Q being less than P plus nu, leaving the symmetric case for future work. Our results also extend earlier lower bounds in the first and second order settings. So in order to highlight our technical novelty, let me now provide a sketch on how we prove these lower bounds. The proof is quite technically involved, and it's okay that you do not immediately understand. You're more than welcome to read the paper for more details. So the idea for proving lower bounds is to construct a function that is both p-order Hölder smooth and uniformly convex, and show that any p-order algorithm needs these many iterations to reach an epsilon approximate solution for this function. For the case of Q being larger than P plus nu, we start by constructing a sequence of non-smooth functions gt as the maximum over some transformations of the coordinates. Since they are non-smooth, we then apply a smoothing operator to obtain capital GT, which, as a result of the smoothing operation, is p-order smooth with parameter h. This step is the most important step, and I'll elaborate on the choice of the smoothing operator shortly. We then add a Q-order regularization to form capital Ft, which then satisfies both high-order smoothness and uniform convexity. Next, we generate the optimization trajectory xt with an algorithm A, which queries up to the p-order oracle of capital Ft at xt to produce the next step xt plus 1. It's important to note that these queries happen on a sequence of functions capital Ft instead of a single function f. But in order to prove a valid lower bound, we need to ensure that this process simulates optimizing a single function f, which we regard as the hard function. We do so by showing that capital Ft is equivalent to capital F in a neighborhood around xt, meaning that any local oracle calls in this neighborhood are equivalent. And finally, with that, we can derive the lower bound on the optimality gap and reach the final complexity by carefully choosing the parameters. Now, back to smoothing. The key for the smoothing step is that in order to derive a tight lower bound, we need the smoothness parameter h to be O of 1, a constant free of the dimension d. Now we examine the suite of such smoothing operators. First, we have the most common uniform smoothing, which samples a noise from the uniform distribution over an L2 ball. Applying uniform smoothing results in h, the smoothness parameter, being the order of square root d, which would lead to a suboptimal rate because in the high dimensional setting, the dimension d is the same order as the number of iterations, t. Next, we have Moreau smoothing. Moreau smoothing gives constant h, but only first-order smoothness, instead of the piece-order smoothness that we desire. Luckily, we have softmax smoothing and Gaussian smoothing that support both piece-order smoothness and constant parameter h. But remember that we require the capital Ft to be equivalent to capital F within some neighborhood of xt. So the query to capital Ft at xt must depend only on local information within this neighborhood. Unfortunately, the domain of both the Gaussian PDF and the softmax function span the entire RD space. Once we apply Gaussian smoothing or softmax smoothing to construct a hard function, evaluating the derivatives of Ft at a point would require global information beyond this neighborhood. To address this and to get the best of both worlds, we propose truncated Gaussian smoothing, a localized variant of Gaussian smoothing. We initially tried truncating over an L2 ball, but due to the truncation operation, the normalization of the Gaussian PDF within an L2 ball once again led to dimension dependence in the smoothness constant. And it turns out that truncating over an L infinity ball resolves this issue, giving us the desired smoothness and locality properties. Plugging this smoothing operator back into the hard function construction framework concludes the proof sketch for the Q larger than P plus nu case. For the other case where Q is less than P plus nu, we generalize the lower bound framework of Argivani et al., adapting the hard function to incorporate general P, Q, and nu. Following their framework, we obtain the tight lower bound for this regime as well. To conclude, we establish tight lower bounds on the oracle complexity of optimizing functions with arbitrary combinations of smoothness order P, Hölder continuity degree nu, and uniform convexity degree Q. In the two asymmetric cases, we leave the symmetric case for future work. Before I end this talk, I'd like to advertise for myself that I'll be on the job market next academic year. I can do both theory and applications for machine learning and optimization. So feel free to reach out to me with opportunities from industry or academia. And I'd also like to advertise for my advisor, Brian. He's super nice, passionate about research, and knowledgeable, and is actively looking for motivated students. Please do not hesitate to reach out to us for collaboration, and if interested, you're always welcome to join us at Purdue. And thank you all for listening. Now I'm open for questions.
All right. Thanks very much for the nice talk and the nice work. Are there questions from the audience? So unfortunately, I can't access the online chat right now, so I'm not sure if that's going to get resolved to this session. I do have a question. So actually, I have a couple of questions, but maybe the first one is that the use of the truncated Gaussian with the L infinity norm was pointed out by several of the reviewers to be a very nice contribution and potentially applicable to other types of theoretical analysis. Can you comment on where that might also be used in other types of problems?
Thank you very much for the question. So I think one key property that we have tried to derive the let me just go to real quick to the page where I have the smoothness operator. There we go. Is when proving lower bounds, and also there are several factors several properties that we care about. The first is the dimension dependence in the smoothness parameter, and the second is how the function after smoothing approximates the original function. The gap between the function after smoothing and also the original function, it is also characterized by probably some d-dependence gap. So there is actually a trade-off between these two. And in terms of proving lower bounds, you need both of them to you need to balance the d-dependence between these two places. And we have actually examined like exhaustively the smoothing operators in the Ducci et al. Paper, if you are familiar with that one. And none of them like basically satisfies our need. So you can actually check our lemma 1 for this smoothing operator, which characterizes very precisely the properties of this smoothing operator, akin to the properties in that paper. And then based on your need, you can like balance the dimension dependence from the smoothness constant, and also the gap between the original function and this function after smoothing. Yeah.
Nice answer. If it's very, very short, yeah.
In this case, where Q equals P plus V, you said this is like intended for future work. So just my question is like, what is an obstacle here that doesn't let you to extend the arguments that you have to this case?
Yeah, that's a very good question. So even as expected as the upper bounds might seem, you will be surprised that to the best of our knowledge, in the realm of lower bounds, only the first order lower bounds exist in this case in the Nestrov's textbook, and which is derived by constructing a hard function and then solve for the square root of the condition number based on solving a quadratic function, basically. We can, of course, in general, extend that to high order settings, in which case you will have a high order equation. The first obstacle is that you do not have a closed form solution to higher order equations. Even if you do, it is like bounded. A third order equation would have a solution to the power of 3. But you might know that the optimal rate in the second order convergence is not 3, but 7/2. So it's actually very challenging to trying to find out how do we get the extra a half. So that's basically the obstacles. Thank you.
Let's thank the speaker again. All right. So just a point of order. If